All right, so eh, you brought us like a whole mountain of information to dig through, and I'm super curious to like really get into it. We're going to be looking at this whole idea of data handling,
Yeah.
which is what these materials call it. And it's all about like the numbers and facts we see all the time,
Yeah.
right? Whether it's the score in a game, your favorite player stats, or maybe just like tracking your own personal records. And like our mission here is to really break down how this information is shown to us and like what it all means. Hopefully by the end of this, you'll be walking away feeling like you've learned a ton, but not totally overwhelmed.
Yeah, for sure. What I think is so cool about this stuff is that it lays out some really, really basic ways we can make data visual,
Yeah.
so we can actually see it. We're talking like simple pictographs, different kinds of bar graphs, and those pie charts you see everywhere. Oh, and we'll even touch on a bit of probability, which is all about understanding the chances behind all those numbers we see.
Okay, cool. So let's kick things off with pictographs. Yeah. These are like the most straightforward way to show data, right? They use those little symbols to represent different amounts of stuff. Like in this example, we're looking at how many cars were made in July, August, and September. And they're using a little car symbol. And each one of those cars equals 100 actual cars. So like just by looking at those symbols, what can you tell me right away about how many cars were produced in July? And without even counting them up, which month looks like it had the most cars rolling off the assembly line?
Okay, so for July, we see like 2.5 car symbols, right? So since each one of those little cars stands for 100 real cars, you know right away that July had 250 cars made. And yeah, just eyeballing it, August has like a whole bunch more of those car symbols. So it totally looks like they were cranking out the most cars that month.
Hmm.
That's what I love about pictographs. They make it super easy to get the picture, literally.
Totally. You can like instantly see what's going on, right? Okay, so now let's shift gears to bar graphs. These feel a bit more like, official or something. They use those bars that are all the same width but different heights to show you like how big or small something is. The source points out that it's important that all the bars are the same width and there's the same amount of space between each bar. So there's this question in the material that says, think, discuss, and write. And it asks, like, what if you just mixed up the order of those bars? Would that change what the information is actually saying? What's your gut feeling on that?
That's a good question. My first thought is that no, like the actual data wouldn't be different. A bar that shows, let's say, 10 apples being sold is still going to show 10 apples, even if you move it to a different spot in the graph. What do you think? Like, could the order of the bars maybe trick people into seeing things differently?
Yeah, I'm with you there. The numbers themselves don't lie, right? But I can see how if you're trying to see a pattern, like is something going up or down, the order of the bars might make it easier or harder to spot those patterns. Like if you're looking for the biggest and smallest values real quick.
Ah, yeah, that's a really good point. The information itself is the same, but how you arrange it can change the story it's telling you visually, right? So regular bar graphs are really awesome for comparing things that are like totally separate categories. Like the order of the bars might be alphabetical, or maybe it's based on the value, so you can see the biggest or smallest one right away. The source has this example bar graph, and it asks some question about the information it shows. Like it asks which year had the biggest jump in students, which year had the most students total, and then there's a true-false statement about how many students there were in specific years. Even without seeing the actual graph, these questions are telling us that bar graphs are really good at helping us compare things across different groups, like years in this case, and we can use them to zero in on specific data points and like see trends over time.
Yeah, you can spot those high and low points super easily, right? Okay, then we've got these double bar graphs, which are like someone took two bar graphs and stuck them together, but like it's not random. They're both for the same categories, so you can compare two sets of information side by side.
Right. The whole point is to compare those two sets of data directly and see how they relate. In the example here, they're looking at how students did in different subjects, comparing their grades from one exam to another. So the questions ask things like, which subject showed the most improvement, which subjects' grades went down, and which ones stayed pretty much the same. Double bar graphs are perfect for seeing those kinds of changes, like did something get better, worse, or just stay flat?
Exactly. You can instantly see for each subject if that second bar is taller, shorter, or about the same as the first one. Now, the source jumps into this try these section, which I think is super cool because it makes us think about what kind of graph would actually be best for different types of information.
Absolutely. This is where you see how to pick the right tool for the job, visually speaking.
Okay, so the first one is all about how many watches were sold over 6 months. They give you the numbers for each month. July is 1,000, August 1,500, September's also 1,500, October jumps up to 2,000, November's the big winner at 2,500, and December goes back down to 1,500. So if you wanted to make a visual for this, what kind of graph would you go for?
Okay, so when you're showing how something changes over time, like monthly sales figures, a bar graph would totally work to show the sales for each month. But honestly, I think a line graph would be even better here. It would really show you that trend over the 6 months. Like, is it generally going up, going down, or just all over the place? You'd see those big jumps and dips right away. And while the book doesn't talk about line graphs just yet, in real life, they're like the go-to for this kind of time-based data.
Yeah, a line graph would totally highlight that trend. Okay, the next one talks about how kids get to 3 different schools. They're looking at walking and cycling, and they give you specific numbers for each method for schools A, B, and C. How would you show that data so it's easy to compare those choices?
This sounds like a job for, you guessed it, a bar graph. But to get that nice comparison between walking and cycling for each school, a multiple bar graph would be the way to go. Like imagine you got 2 bars for school A, one for walking and one right next to it for cycling. Then you do the same for school B and so on. So you can easily see if more kids walk or cycle to each school and also if there are any like overall differences in how kids travel to the different schools.
Right. That side-by-side thing for multiple categories makes total sense. Okay, last one in this section. We've got the percentage of wins for 8 different cricket teams. And they're comparing their wins in the Champions Trophy and World Cup back in '06 to how they did in the last 10 ODIs in 2007. So they give percentages for each team in both of those periods. What would be the best way to show that?
Oh, this one's easy. A double bar graph all the way. You'd have 2 bars next to each other for each team. One bar would show their win percentage in those big tournaments back in '06, and the other bar would show their more recent record. Bam! Instant visual comparison of how each team's performance has changed. You could tell right away who's gotten better, who's slipped, and who's stayed pretty much the same.
Perfect example of how the question you're trying to answer with the data should tell you what kind of graph to use. Okay, now let's get into circle graphs or pie charts. Those always make me think of like cutting up a pizza or something.
That's a great way to think about it. The whole circle is like 100% of whatever you're looking at, and each slice of the pie represents a piece of that total. The bigger the slice, the bigger that piece is compared to the whole thing.
So the source has this example of a kid's day. They say the kid sleeps for 8 hours out of 24, which is like a third of the day. And then they're at school for 6 hours, which is a quarter of the day. So those fractions tell you exactly how much of the pie chart each activity gets, right? And if you add up all those fractions for all the activities, they should always equal one whole pie, or like 100%.
You got it. It's a really easy way to see how different parts contribute to the whole picture. Now the source throws another try these at us, this time with a bunch of pie charts. And it wants us to figure out what fraction of the circle each slice represents. Even if we can't see the actual charts, the main idea is knowing that each piece of the pie is like a proportion of that whole circle.
Okay, and then there's an example of a pie chart that shows what kinds of TV shows people are watching. And the questions ask which type of program is the most popular, and then which 2 types of programs, if you combine them, have the same amount of viewers as sports channels. So this shows how pie charts are really good at helping you quickly pick out the biggest and smallest segments and see how different categories stack up against each other.
Exactly. Like you can instantly see how important something is just based on how big its slice of the pie is. Now, the source actually goes into how to make these pie charts, and that involves a bit of geometry, specifically working with angles.
Time for some math. So they use this example of favorite ice cream flavors. Chocolate gets 50%, vanilla gets 25%, and all the other flavors combined also get 25%. How do you take those percentages and turn them into those pie slices?
Well, think about it. A circle has 360 degrees, right? So to get the angle for each slice, you just take its percentage of the whole thing and multiply that by 360 degrees. So for chocolate, which is half of the pie, you do 0.50 times 360 degrees, which gives you 180 degrees, which is a straight line cutting the circle in half. Vanilla at 25% would be 0.25 times 360, which works out to 90 degrees, a right angle. And those other flavors, also at 25%, would get another 90-degree slice.
So you draw your circle, find the middle point, draw a line out to the edge to get started, and then you grab a protractor and mark out those angles, drawing lines to make those pie slices.
All right.
Got it. The book then goes through this example of how a family spends their money each month, and they give the percentages for different categories, including savings. One of the questions asks how much money they spend on clothes if they save 3,000 rupees each month, which is 15% of their total budget. How do we crack that one?
Okay, so that's a good example of how knowing about proportions can be really useful. If 15% of their budget is 3,000 rupees, and we know clothes are 10%, we can figure out their total budget first. So if 15% equals 3,000, then 1% would be 3,000 divided by 15, which is 200 rupees. So then their total budget is 100% times 200 rupees, which comes out to 20,000 rupees. Now that we know the total, we can figure out how much they spend on clothes, which is 10% of 20,000, which is 2,000 rupees.
Okay, so you're using the percentage and value we know to find the missing piece. Makes sense. The next example looks at what a bakery sells, and this time they give you the actual amounts in rupees for each item, not percentages. So you'd have to figure out what percentage each item represents before you could calculate the angles for the pie chart.
Right on. You take each item's sales, like let's say regular bread is 320 rupees, and divide that by the total sales, which in this case is 720 rupees. That tells you what fraction of the total money came from regular bread. So 320 divided by 720 simplifies to 4/9. Then, to get that angle for the pie slice, you multiply that fraction by 360 degrees. 4/9 times 360 equals 160 degrees. You do the same thing for each of the other items, fruit bread, cakes, biscuits, and whatever else they're selling, using their individual sales numbers.
And then there's this other try these, and it's about how a kid spends their day, like how many hours they spend on different activities. It's like 24 hours total. And they break it down into sleep, school, homework, play, and other stuff. So the first thing you gotta do is turn those hours into fractions of the whole day, and then use those fractions to figure out the angle for each activity, right? So you could draw the pie chart accurately.
You nailed it. You're basically converting those raw numbers, the hours, into a proportion of the whole day, and then that proportion tells you how big to make each slice of the pie. Now, this brings us to a really important question. How do you know which type of graph is the best one for the data you're working with? The book has this think, discuss, and write section again, and they give us 3 different situations to think about.
Okay, so the first one is about how much grain they produce in a certain state over a bunch of years, from 2001 to 2006. And they give you the specific amounts for each year. It's kind of like that watch sales example we talked about earlier. What kind of graph would you use to show that?
We talked about it before, and I think it still holds true. A line graph would be perfect for this. Since you've got data points that were collected over time, over those years, a line graph would really show you any trends in how much grain they were producing. You could instantly tell if production was going up, going down, or just bouncing around, and you'd see any big jumps or drops right away.
The second situation is about what kinds of food people like. They've got this group of 120 people, and they give you the numbers for how many people like North Indian food, South Indian food, Chinese food, and then other types of food. What would be the best way to show those preferences?
For this one, where you're comparing different categories and seeing how popular each one is, either a bar graph or a pie chart would be a good choice. A bar graph would clearly show how many people liked each type of food, so you could compare those numbers directly. A pie chart would instantly show you what percentage of the whole group liked each option, giving you a sense of their relative popularity. Choosing between the two just depends on whether you want to highlight the actual numbers or the proportions.
Right, sometimes you want to see the raw numbers, and sometimes the percentage is more useful. Okay, last one in this section. They give you the daily income of workers at a factory, and they break it down into different income ranges, like 75 to 100 rupees, 100 to 125, and so on. And they tell you how many workers are in each range. What kind of graph would you use to show how that data is spread out?
This one calls for a histogram. It's like a special kind of bar graph that's made for showing how continuous data is distributed, like data that falls into specific intervals or ranges. One way you can often tell it's a histogram is that the bars are usually touching each other, which shows that the data is continuous. The height of each bar tells you how many workers have an income within that particular range, so you can see how incomes are distributed across the whole group.
That's super helpful. Now, I know when to use a histogram versus a regular bar graph. So the book then briefly mentions something called Exercise 4.1, and it basically gives us a sneak peek into how these data tools are used in real-life situations. They mention stuff like figuring out what a pie chart is saying about what kind of music people prefer, analyzing votes to see what people's favorite seasons are, showing people's favorite colors in a pie chart, and understanding a pie chart that shows students' grades in different subjects. So it's basically like real-world examples of how we use these visuals every day.
Totally. These exercises really show you how practical it is to be able to understand and create these different types of graphs so you can communicate information effectively and get what those visuals are trying to tell you. Okay, now we're going to switch gears a bit and move into a related but kind of separate area, the idea of chance and probability.
So this is where we start thinking about how likely things are to happen. The source kicks things off with some everyday examples of chance, like forgetting your raincoat on a rainy day, getting a test question about a chapter you didn't study, or a train that's usually on time being late. What I find interesting about these situations is that it's not like all the outcomes are equally likely, right?
Right, you got it. There's that element of the unknown, and depending on all sorts of factors, some outcomes might be more or less likely to happen than others. So the source contrasts those examples with what they call random experiments, where each possible outcome has an equal chance of occurring. Like the classic example is flipping a fair coin, heads or tails is 50-50.
And then there's another think, discuss, and write section. And this one wants us to think about other examples of those random experiments. They mention trying to start a scooter, rolling a regular six-sided die, spinning a wheel that's divided into sections, and picking a ball out of a bag that's got different colored balls in it, but you can't see inside. So with each of those, you can list out all the possible results, and if everything is fair, like the die isn't loaded, the wheel's evenly divided, and the poles are all the same except for their color, then each outcome has the exact same chance of happening.
Right. And the source also brings up this super common misconception about probability, especially when people are rolling dice. It emphasizes that each roll of the die is a totally separate event. So even if you roll the die 10 times and don't get a 6, the chance of getting a 6 on the next roll is still the same 1 out of 6. What happened before doesn't change the odds for the next independent event.
Yeah, that's a really important point about how each event stands on its own. So the source talks about equally likely outcomes, and how if you do a random experiment over and over again, like flip a coin a ton of times, the number of heads and tails you get will start to even out. Same thing with rolling a die. If you roll it enough times, each number should come up about the same number of times.
That whole idea of equally likely outcomes and doing experiments lots of times leads right into how we define probability. So let's go back to that coin toss. The probability of getting heads is the number of outcomes where you get heads, which is just 1, divided by the total number of equally likely outcomes, which is 2 heads or tails. So the probability of getting heads is 1 out of 2, or 1/2. Same idea with a fair die. The probability of rolling any specific number, like let's say a 2, is that's the one favorable outcome divided by 6, because there are 6 equally likely outcomes. So it's 1 out of 6, or 1/6.
Okay, so just to make sure I'm getting this, what would be the probability of rolling a 5 on a normal die? And what about rolling a 7? Or rolling any number between 1 and 6?
The probability of rolling a 5 is also 1/6. Same reasoning, one favorable outcome. 6 total possibilities. Now, rolling a 7 on a regular die, that's impossible. There's no 7 on a die, so the probability is 0. But if you're talking about rolling any number from 1 to 6, well, that's a sure thing. It's got to be one of those numbers, so the probability is 6 out of 6, which is just 1, or 100%.
Okay, now I get it. So now the source introduces this idea of outcomes as events. It says that an event can be a single outcome, like getting heads, or it can be a group of outcomes. Like rolling an even number on a die would be considered an event because it could be a 2, a 4, or a 6. And there's this try these question that asks exactly that. Is getting an even number on a die an event?
Yeah, totally. Getting an even number is an event because it covers those 3 specific outcomes. And since there are 3 ways to get an even number 2, 4, or 6 out of 6 total possibilities, the probability of that event, rolling an even number, is 3 out of 6, which is the same as 1/2, or 50%.
The source then gives this example of a bag with 4 red balls and 2 yellow balls. If you reach in and grab a ball without looking, what are the chances of picking a red ball compared to a yellow ball?
All right, so there are 6 balls total, so there are 6 possible things that could happen when you pick one. Since 4 of them are red, the probability of grabbing a red ball is 4 out of 6, which simplifies to 2/3, and there are 2 yellow balls, so the probability of picking a yellow one is 2 out of 6, or 1/3. So you can see from those probabilities, 2/3 is bigger than 1/3, you're more likely to get a red ball.
And they've got another example with a spinning wheel, and they ask about the chances of the pointer landing on a green section and the chances of it not landing on a green section. So to figure that out, you need to know how many green sections there are and how many total sections are on the wheel.
Exactly. The probability of something happening is always the number of ways it can happen divided by the total number of equally likely things that could happen. Now, the source brings these ideas of chance and probability back to everyday life, which I think is really cool.
Yeah, they talk about how we use the word chance all the time, like,
Yeah.
what's the chance of rain, especially when you've forgotten your umbrella. And they point out that this idea of chance can often be expressed as a probability. Like, if it rains, on average, 1 day out of every 10 during a particular season, you could say there's a 1 in 10 chance of rain, or a probability of 1/10, which also means there's a 9 in 10 chance that it won't rain.
And then they highlight two super important ways that probability is used in the real world. The first one is exit polls during elections. They ask a small group of people how they voted as they leave the polling place. And then statisticians use probability to predict who they think is going to win the whole election.
The second one they mention is weather forecasting. The meteorological department uses a ton of data about past weather patterns in these complex models based on probability to estimate what the weather's going to be like in the future.
Hmm.
So when they say there's like an 80% chance of rain tomorrow, they're using probability calculations to figure that out.
For sure. Probability is this essential tool that people use in a lot of different fields to try to predict what's going to happen and assess risks. The source then mentions exercise 4.2, which has a bunch of different probability problems, like listing all the possible outcomes of an experiment, figuring out the probability of specific events when you roll a die or draw a card from a deck, and working with probabilities related to picking things from a set or spinning a wheel that has different possibilities. So these exercises are all about getting hands-on practice with calculating and understanding probabilities.
Finally, the source kind of wraps things up by summarizing all the key ideas we've covered. It reminds us how important it is to organize data in a systematic way, how circle graphs are used to represent parts of a whole, how to think about experiments where every outcome has the same chance of happening, and how probability is calculated. It also goes over what we mean by an event and how chance and probability show up everywhere in our lives. It's a really nice summary of everything we've talked about.
It brings together the two main things we've been exploring in this deep dive: how we use visuals to represent information so we can understand it better, and how we use probability to figure out the likelihood of different events. Both of those are super important for navigating the world around us.
Well, we really hope this deep dive into data handling and probability has been helpful. It's amazing how these seemingly simple ideas underpin so much of how we look at and interpret information.
Totally. And it makes you think about how often we're already kind of intuitively making judgments about probability in our everyday lives, even if we don't realize it. Like, what are some of those hidden probabilities that might be shaping our decisions and what happens to us more than we think? I bet if we thought about those hidden probabilities, we might come up with some pretty interesting insights.